Um, Good morning. My talk today is about the topological characterization of MOFs in the CSD MOF subset, and there's a couple of MOFs here, just to show the crystal structure of these materials and why they're suitable for topological identification. What are MOFs? Well, I'm sure most of you are already very aware of what MOFs are, but they're these customizable, highly porous crystal structures where we have metal nodes connected by organic linkers, and in 1, 2, or 3 periods, typically. So we know the atomic positions of the atoms in these materials, and we can use them to sort of simplify a very complex MOF into an underlying basic net. And we can see how other materials, even though they're connected with different organic structures, as demonstrated in this picture, are underlyingly connected. Where are all these topologies found, or these underlying connections found? Well, there's a database called the Reticular Chemistry Structural Resource, and this work was done probably 15 or almost 20 years ago to sort of determine all of these connectivity potential nets for porous materials. And it wasn't just the MOFs that they had in mind, they also considered COFs and zeolites and other sort of aluminium phosphate style structures. But this is something that we can apply to MOFs particularly, and hopefully this will give us some insight into sort of like the limitations of pore size for certain materials, and the mechanical stability of materials. So in the CCDC or the CSD database, there are probably around 100,000 MOFs. I think the latest release, there was about 120,000 MOFs, and about 86,200 of those were non-disordered MOFs. And we really do sort of need to take into consideration the presence of disorder when we're trying to sort of simplify the connectivity of these materials. Here are a few examples of MOFs within the CSD that we've actually categorized the topology of. And there are other projects which have done this before as well, with varying levels of success. Actually, at this conference that I'm attending this week, there was a paper from University of Paris where which is in preprint in Chem Archive right now, where they've also started to develop their own topological identification tool. Yeah, as I was saying 2 slides back, there are 1, 2, and 3D MOFs within the MOF subset, and some very recent work at CCDC has seen the introduction of these subsets into conquest, so you can actually have a look at these subsets yourself in the drop down selection of database menu. And what we actually find is that the majority of MOFs in this subset are actually one-dimensional wires, that for the topologist is not very particularly useful, considering they only expand in one dimension. This can be an interesting topic because some of these are like hollow tubes. So the way that these tubes are constructed could be of interest to topologists, and nobody actually at the moment seems to be categorizing these one-dimensional MOFs into sort of a topological set. And in the RCSR, there are actually about 13 or 14 different possible sort of tube-like configurations of 1D MOFs. So what we did was we took these MOFs and we ran them in a program called MOF-ID, which was designed and developed at Northwestern University in Chicago. And what we found was we managed to actually give 2-dimensional topology to 6,000 of these 22,000 2D MOFs, and that gave us a success rate of about 28%. And as you can see, there's a very, very dominant topological type in 2D MOFs, which is SQL, and that's a very, very simple sort of square lattice type of topology. And following that, HCB, which is a honeycomb sort of shape, is the second leading 2D topology. And then we also did this with a 3D topological set, and the success rate, despite there being more MOFs, was actually considerably less. Again, we can see that there are a high hit rate for square lattice type topology. Well, this is unusual because you wouldn't expect to see a two-dimensional net in a three-dimensional set of structures. And here we can see that it actually is the top performing or most frequent topological type. And this could be due to a number of issues, but we suspect that it's down to the software which is contained within MOFID and that is used to bond the atoms together. So the method that it uses is to upload a crystallographic information file, a CIF file, and it chooses to assign bonds based on estimates, I suppose. Whereas in CCDC, you can actually see, and here's an example, this structure, Bogness. We can see there's a connection between these two rings here in the CCDC's version of this structure. But when we actually take that file and download it and we upload it again into a topological assignment program, and the bonds are assigned, we actually find that this bond is missing in every software that we've put this structure into. And that's really important that this bonding is correct, particularly for linkers, because it's going to change the topological assignment of the structure. We note that in the 2D Sheets database, there are actually quite a few 3D MOFs which have been identified, and that's typically because in the file we have a few two-dimensional layers which are stacked on top of each other, and because of the close proximity of the layers and the lack of bonding information in the CIF file, that actually presumes that these layers are bonded together, whereas we know that they aren't. So what we want to do is achieve accurate and consistent topological characterization for these periodic MOFs, and hopefully we can gain some new insights into the properties that this has an impact on. So how do we want to improve the topological characterization? Well, we want to take this bonding information from the CCDC, and we want to try to run it in the CSD's Python API. Why would you disregard this bonding information when it's available to you? So yeah, as I was explaining, the CIF has no bonding information. We get incorrect bond assignment at this middle stage here, and then the final stage where topology is assigned is we get consistently errors and problems. So here I'm going to show you an example of a 2D MOF within this new 2D MOF subset. Here you can see it's actually two separate two-dimensional sheets which are closely layered together. And we thought, this is strange. Why is this structure being given a three-dimensional topology by this topology assignment software? And here, if we expand it, just make it a bit larger, you can actually see it definitely, there's no connections in between the layers. So what we did was we thought, well, what's causing these layers to bond together? And we assume that it's the silver atoms which are being bonded across layer. This cross-layer bonding. So we just increased the limit of the bond distance very slightly from 3.23 to 3.35. So just over 0.1 increase there. And as you can see, this 2D MOF becomes a 3D structure, which is obviously incorrect. And it's not unlikely to assume that this happens to many structures within the CSD subset when their bonding information isn't present. So what we're aiming to do is, I just highlighted that bond there. What we're aiming to do is obviously avoid these. And here are a few more examples of where this actually happens. So all different types of structures, and they're given all of these topologies here, as you can see, JEA, CRB, TFA, GRA. And what's interesting is that the one in the top left and the one in the bottom right are actually very, very similar structures. And when the bonding information isn't present and the bonds are assumed, we actually get two different three-dimensional topologies, which is very unusual. You wouldn't expect them to be given two different topologies. They look very, very similar. They look the same in the way that they're bonded together and the pattern of the crystal structure. So the solution, as I was saying, is to actually take this bonding information from CCDC directly. And we've been doing that, and we've been trying to sort of figure out a way for us to break these structures down. There are actually about 6 or 7 different algorithms that have been proposed, and there's even a new one in this most recent preprint paper. So what we do is we try to simplify these metal nodes into a single point, and then the link has become branches. So here you can see we take this BedJect structure on the left, we simplify it in the middle, and you can see how the connectivity of this structure is corresponds to the actual material. And then we can actually use this file and overlay it in Mercury, for example, and we can view the structure on top of it itself, so we can verify that that's actually correct. And we do the same with the torsion N at the bottom, and you actually get some really nice looking figures here for all different types of material. So here's one example of where we've actually taken a structure that isn't topologically identifiable by these programs, and we think that it should be. So we actually made the first topological assignment of this Vatnik structure. In MOFID, we were getting bonding issue errors, and in Topos, we were getting all sorts of disjoint structure representations where there was no topology assigned. It was assuming that this material was actually broken into clusters, and we simplified it using this new Python software that we're looking into, and we ran it in Sister, which is a GraphNet matching program written in Java, which is from the Sheffield University. And this has been around for quite a long time. It's part of the Gavrog project. I think it probably published around maybe 10 years ago. And we actually get the SRS topology for this structure. And when we get the simplified net and we overlay it in Mercury, we can actually see that this corresponds to this structure. And one of the things that is very difficult is actually to confirm the topology of materials, because well, you have to do it visually. You have to look at it yourself. And if you're not a particularly experienced topologist, this can be something that's very, very difficult. There are over 2,000 different possible three-dimensional topologies in the RCSR. So why are we doing this? What are the applications of topology? Well, there are quite a lot of areas of interest, particularly with creating hypothetical computational MOFs. So we could actually, for example, take a known conductive linker, and we could try to build structures in all different topological configurations. And if we do that, we can investigate whether certain topologies have more conductive properties using the same materials, and we can actually look at things like porosity, how the porosity of materials might change or might be limited. So here are some examples of work that's been done with topology so far, and obviously we hope that more and more works will start to emerge as this tool is developed and hopefully used by the MOF community. So Tobacco, which is from the Colorado School of Mines, is a topology-based hypothetical MOF building software where they take underlying topology and they build MOFs with building blocks. So you can choose certain metal nodes, so you can actually make them in Material Studio or whatever program that you prefer, and self-assemble them using this package. We also note that there's some work from the Topos group, which is investigating porosity and against topology. And they actually found some interesting trends. We can also use topology to tune the apertures of the MOFs and calculate the mechanical stability, or we can investigate the mechanical stability of different topological MOFs as well. So to summarize, what we're trying to do is develop a tool which is compatible with CSD's Python API to access the information that's contained within this CSD. I mean, this information is there, so why not use it, right? And then we want to create some outputs for visualizing all of these different structures. And there's loads of ideas in that sort of area. Yeah, as I've showed you some of the underlying nets which are layered on top of the actual structure. Another thing that we could look into is actually looking at augmented reality files. So if any of you are familiar with Unity, we can actually use Unity to put a topology, a 2D or a photograph, for example, or a QR code, and you can use an app on your phone, and you could look at the topology in 3D using your phone on a screen, which is actually really quite interesting development. So things to consider in the future is we could actually use this topology information in the CSD to create subsets of MOFs based on the topology. Say, for example, you're really interested in the CSQ topological type because of its particularly large pore sizes. Then we could, download all of the CSQ MOFs from CSD MOF subset, and we can also use this. Hopefully, this tool in other areas of chemistry, for example, COFs or aluminium phosphate structures or zeolites. And this most recent paper from the university in France has actually started to do that, and they've looked at several different databases of non-MOFs to characterize topology with those two. And we also want to try to use high throughput calculations to establish trends between topology and all sorts of different properties of MOFs. So I'd like to thank the CCDC, obviously, for funding this project, and my supervisor, Payman, for his support, and also Jason, who's my supervisor at the CCDC, and the University of Sheffield.
Well done, Lawson. Give you a round of applause. Well done. Okay. So I think, thank you very much for managing to get in from, so very early in the morning over there in Colorado. Are there any questions for Lawson? No one. Okay. So I feel guilty asking you a question because I'm one of your supervisors. But I guess, I mean, the silver example is actually quite an interesting one, I think. Because there are challenges in connectivity and bond typing, and I wonder whether there's a perspective or if we have an idea of how common that is within the CSD. So I mean, I think it's a challenge really also for us as well in our editorial efforts as to whether we decide something is a bond or it isn't a bond going forward. And I know that particularly with silver, it's very, very challenging. So did you have a feel for the sort of how many structures are being affected by that type of thing?
Well, from what we know of successful topological assignment, say for example in the 2D subset, from what I remember, I think there's about 300 structures out of 22,000 which have been given 3D topologies. So it's probably less than, it's probably about 1 to 2%, which doesn't sound very much, but when we're dealing with 100,000 MOFs, it's actually a considerable amount, I suppose.
Yeah, and I think oh, Simon's got a question. I'll come to you in a minute, Simon. I think it is an interesting challenge to deal with. Simon, your thought? Go ahead.
Yeah, thank you very much, Lawson. I was interested in what you said about topos giving you strange bonding. Is this when you generate its? I think it calls it the adjacency matrix.
This is using the. Sorry. Yes. Go on. Sorry.
No. Go on.
Yeah. Well, what you do is you use the the adjacent. It's called the auto CN function, which is an automatic connection of bonds. Yeah.
Yeah, that's right. So we see this sometimes, that you get strange clustering going on, and you have to change the method, the algorithm that it uses to generate the adjacency matrix. They've got I think there are 2 or 3 of them. There's one called the method of sectors and another one called something else, and the manual's absolutely no use to you at all, because it will just tell you click this button to apply the method of sectors. But have you tried fiddling with that. I mean, they're using a different algorithm, and I wonder whether your results improve in Topos if you use a different one.
Yeah, good question. Firstly, yes, I agree that the manual is not very useful. And one thing that's very annoying is that you don't really they don't really describe the techniques that they're using, other than they give them a name. You know, there's not very much transparency in sort of the algorithms that are contained within this software. For us, we want to try and do a high throughput method. So Topos isn't very suitable for that, unfortunately. I suppose you could actually try the approach using different algorithms in Topos, but it would mean rerunning the program again and again. And
I think you can run it on lists. I think he calls this continuous calculation.
Yes, you can, but it's not. I've actually tried using Topos for 100 zirconium oxide MOS structures, and what I found was that when I ran them using the continuous calculation box ticked, it actually gave me quite a few errors. And when I ran them individually using exactly the same technique, it actually assigned topology, which I found very strange. So I don't really know.
This sounds all too familiar, and it will sound familiar to Pete too, because I remember when he was doing his PhD, he tried to. We used Topos for that as well, and it was. I think all of this is sounding desperately familiar. But if you're seeing strange connectivities, then just try and changing its algorithm for generating the adjacency matrix.
Yeah,
so it might start making more sense.
So
go on, Lawson.
So actually, at this conference, I was at talk yesterday, and they were presenting a new software, which is a Julia software, and apparently that's they actually told me this is what all the kids are using these days. So I thought, well, probably good for me then. And
is this from Topos Group?
No, this is from a different university. It's a University of Paris. And they were saying that they're sick of trying to use Topos because of all the different dilemmas that you sort of run into, and they've decided it was easier to develop their own topological identification software than it was to continue to use Topos. And I haven't actually, I've read their paper in preprint yesterday. It's in Chem Archive at the moment, and they're very, it's very exciting actually, because it looks like they're allowing you to upload any sort of file. So you could upload a mol2 file or a CIF file, and they have actually developed 6. They're using 6 different algorithms, and they've actually tried to sort of interpret the algorithms used in Topos and finally sort of publish an explanation of what's going on.
I see. Yeah.
And they've also developed their own algorithm as part of that project as well. So it'd be interesting to see how that new software would actually perform against the MOFs that we've been running in MOFID and in Topos.
Yes,
indeed. So
thank you very much, Lawson.
Thank you, Lawson. So